Many real-world objects such as wreaths, plants, corals, and insects have intricate shapes. They exhibit severe occlusions and numerous thin structures and discontinuities. Automatically acquiring complete 3D models of such objects is important for computer graphics applications. In theory, a shape from silhouettes approach may be used to reconstruct the visual hull of intricate objects, provided we have a sufficiently large number of views. An easy way of capturing a large number of silhouettes is illustrated here. A small light source is moved around a stationary object, and the shadows cast by the object on a single planar rear projection screen are imaged by a camera. The key observation here is that the relative transformation between the screen, or the image plane, and the object remains fixed as the light source is moved. We use the term shadowgrams for these shadows, and the term coplanar shadowgram imaging for the system. The physical setup used in our experiments is shown here. The light source positions are estimated using the shadowgrams of at least 2 spheres. The acquired shadowgrams can then be used to recover the visual hull of the object. Consider this wreath-like object with numerous thin and occluding branches. If the number of views is small, the visual hull obtained is too coarse and does not represent the detailed structure of the object. On the other hand, the visual hull obtained using 50 shadowgrams is an excellent 3D model of the real shape. Here we demonstrate the sensitivity of visual hull estimation in the presence of errors in light source positions and silhouette contours. As shown, the estimation worsens significantly for a large number of views. We now show a rendering of this model using Maya. Notice the sharp shadows of the small branches. Next, we show the results of applying our technique to a wiry polyhedral ball. 45 views were used in this experiment. We now trace the progression of our optimization algorithm for this object starting from the erroneous reconstruction. The match between the acquired and reprojected silhouettes increases until it becomes almost perfect. We now show a rendering of this model using Maya. Now we show the results of applying our techniques to 2 plastic palm trees. 50 views were used in this experiment. We now show a rendering of this model using Maya. In order to evaluate our techniques, we've performed several simulations using objects with known ground truth geometry. In all cases, we've added a small random error to the light source positions. First, we show a seaweed-like object with many thin and self-occluding branches. Notice the significant improvement in the reconstructed 3D model. Here we trace the improving light source positions. The match between the acquired and reprojected silhouettes increases until it becomes almost perfect. We now show a rendering of this model using Maya. And a comparison to the ground truth model. Next, we show the results for a spider with thin legs. "80 views were used in this experiment. Finally, we show the results for a bicycle with many thin spokes and intricate gears. "60 views were used in this experiment. In summary, we have presented a practical approach to capturing accurate 3D models of intricate shapes.